Okay, so a little more on circular motion. So according to Newton's first law, the object wants to keep moving in a straight line unless acted on by the outside force. All right. So we're going to keep it going at that constant speed, okay, directed towards the center of the circle. So the force is going to have to be what causes this change in direction on the object. So here's an example where we've got tension. So there's a string between the person's hand and the ball. So the ball has a tension inward towards the person's hand, but the person feels, because of Newton's third law, a tension outward. So the force acting on the ball is always going to be perpendicular to the motion of the ball. So if I was to kind of draw what's going on here, like dot, 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 I guess it really goes bigger circle. But the ball would be going around like this, and this would be a perpendicular angle here. It's going to change the ball's direction, but not the speed, right? And it is that center-directed force, okay? Centripetal, right here, means basically center seeking, okay? Centripetal, center seeking. Now, to understand a little bit of what's going on here, we need to understand a little bit about circles, because that's our path, and then think about velocity. So the path we're taking, every revolution is the circumference. So we're going 2 pi r every circle or every path we go around. All right? Now, we've got two different ways we can talk about the time for a revolution. We can talk about the revolutions per time, the RPM or the RPS. That's the frequency. Or we can talk about the period, the time per revolution. All right? And we're used to dealing with velocity, right, as just distance over time. Well, in this case, our distance is the circumference and then our time, well, we can either think of our time as the period for those revolutions or as the frequency for those revolutions. All right? So we either end up with 2 pi rf or 2 pi r over period. Those are our two possible definitions for the velocity of something with circular motion. All right, so again, just to revisit this piece. So when the object is in circular motion, right, the acceleration radial is v squared over r. Right? The force centripetal then has to be the mass times that acceleration radial. And then that would be mv squared over r. So a key thing here is that centripetal means center seeking. You may have heard the term centrifugal. Okay, probably because the device is like a centrifuge. That means center fleeing. They are a device that does not actually, have a real force on it. They're just demonstrating Newton's first law, that things want to keep going in a straight line. The reason we think that there's a centrifugal force there, which there isn't, is because we're experiencing Newton's third law. All right? So centripetal is the actual force being experienced, or a type of force is being experienced on the object. So in this case, the ball has a centripetal force on it, caused by the tension in the string. All right, so tension is providing our centripetal force. For a planet, it's gravity causing the centripetal force. When you're in a car driving around a curve, it's friction causing the centripetal force. All right, so different forces actually cause the centripetal force. All right, but centrifugal, that's that false force. It's just a perception of inertia. A visual way to understand this is, if it was centrifugal, things would just fly off outward, and they don't. If you were to let go of that string, or the string was to break, it keeps going in a straight line off the path. Okay? It doesn't fly outward. It just goes in a straight line. It stays going tangent to the circle. All right, so this is now going to bring us into the idea of circular orbits. Okay? So the curvature of the Earth, because again, the Earth isn't flat, sorry to surprise some of you, basically drops 5 vertical meters for every 8,000 meters tangent to the surface. Okay? So that means if I was to launch something perfectly straight and it was going fast enough that it was going to take it 8,000 meters before it should have had a vertical change of 5 meters, that object would never actually hit the ground. That object would be in an extremely low Earth orbit. So one of the things Newton had actually, kind of hypothesized based on this idea of the universal law of gravity was, what if you shot a cannon or a gun fast enough from the top of a mountain or something? Could you actually end up hitting yourself in the back of the head or actually launch something into orbit? So a satellite is basically something orbiting the Earth. in circular orbit would just be something launched fast enough to ensure that it's falling at a rate that matches the curvature of the Earth. So if I could, for every 8,000 meters of horizontal change, ensure that I only had 5 meters of vertical change close to the Earth's surface, I would be in very low Earth orbit. So now, to actually have a circular orbit, certain factors matter. So positioning. So beyond Earth's atmosphere is generally where we like to orbit because we reduce the air resistance there. Okay. So we've got two kind of main areas where we like to launch things. What we actually call true low Earth orbit, which is about 150 kilometers or so above Earth's surface. Okay, so our actual distance there, okay, here the distance would be the radius of Earth plus this 150 kilometers. Okay, so it's the distance you're at in terms of gravity. All right, so the acceleration due to gravity there isn't 9.8, so it's less based on our equations. That's where we'd like to orbit for low Earth orbit. So this is where like the International Space Station is, a lot of our telecommunication satellites, kind of at that place. Then we get to our geostationary orbits. So these are a lot of our weather satellites. Okay, so these would be the ones that are at a distance of the radius of the Earth plus 35,000 kilometers. Okay, so that's how high above the Earth they are. And with geostationary versus the low Earth, it's going to change the period, all right? Because again, that motion is trying to keep it so that gravity is perpendicular to their motion. Because we try to keep them in fairly circular orbits. So for low Earth, it takes about 90 minutes for it to go around once. For geostationary, it's exactly 24 hours because we want it to stay exactly over the same point on Earth at all times. Okay, so this brings us into Kepler, or the start of Kepler. So what we actually find out in the real world is not every orbit can be a perfect circle. So you might go a little bit above the required speed to be in the perfect circle, which gives you an ellipse, gives you an oval path. All right. So an ellipse is when you have two foci, right? So I've got my foci here and my foci here, and I kind of go around based around those two foci points. Now, so a circle is just a special case when these two foci merge together into the same point. So what happens for a lot of actual satellites, and even planets for that matter, because a planet's technically a satellite of the sun, is this elliptical path forms where you're going slightly greater speed at one point, you go away, you slow down, and then you come back around, and then you speed up again as you come back around, and then you repeat the process over and over again. So a lot of satellites are close to circular orbit, but they are still off a little bit. Their orbits aren't perfect circles, they're slightly elliptical. And again, the same is true for most planets, they're slightly elliptical. So there's a focus point, which is where the main orbit is based off of. So for like the Earth, one of our focus points is the sun. Another point is slightly shifted from the center of the sun. We basically speed up, slow down just slightly. So this gets us truly to Kepler. So what Kepler discovered as Tycho Brahe's assistant was basically 3 laws that govern planetary motion. So it's a very interesting story because Kepler was really just a really good mathematician. Brahe was a really good observational astronomer. And somehow, through their relationship, Kepler had gotten all the data, was analyzing it for Brahe, and then Brahe dies, mysteriously. Some people suspected Kepler killed him, some people suspected one of Brahe's cousins killed him. But needless to say, not too long after Brahe's death, Kepler publishes finally. And the main thing he figured out from the data was that the motion of the planets were not circular, they were elliptical. Once he figured that out, he formulated the following 3 laws. So first one was kind of easy, that the path of each planet around the sun was an ellipse, and the sun was the focus of the ellipse. Okay, so here's an example, a little drawing here where the sun is one of the focuses. Technically over here somewhere would be the other focus. okay? But we really don't care about that. We just really care about the sun. Now, the second that he figured out was that the line from the sun to any planet sweeps out an equal area of space in an equal time interval. So let's just say that this from here to here is 1 month. Okay, from here to here would also be 1 month. Okay, if you look from the arcs obviously look like different arcs, but because you've got a different dimension here and here, these two areas are equal. All right. So whatever area is swept out of that ellipse every month, it's kind of a geometry, relationship that he figured out, they'd sweep out the same area, okay? And that's because you're going faster at one point, slower at the other. You're further away at one point, you're closer at the other. So we end up with equal areas. Now the third is where it gets a little more complex, because how he actually figured out these laws was he had been looking at orbital data. And this is what Brahe had gathered over all these years. He had looked at the periods for the planet's orbits, and he had looked at what's called the semi-major axis. Okay, so the semi-major axis is, just to kind of look on the diagram here, this distance here. Basically, for an ellipse, the center to kind of longest point distance, all right? That's the distance he had. And all of these have been converted out of meters into something called the astronomical unit, right? And if we look on the chart here, it's kind of probably hard to see, but 1 AU equals the Earth-Sun distance, okay? So we defined everything based on how far the Earth is from the Sun. So 1 year for us going around the Sun is 1 year for Earth, and then the Earth-Sun distance is 1 astronomical unit. So we defined everything based on Earth. But he figured out this relationship that the period squared, t squared, was approximately the same number as that semi-major axis cubed. Right? And that's what this little chart shows. It's a bunch of period squared semi-major axes cubed. So that meant if you have two planets that you want to compare, because if these numbers are basically the same, the number over the number will be a constant. And that constant is the same for all planets orbiting the Sun. If you go to a different star, it'll be a different constant for that star. But this t squared over a cubed relationship, this would be like planet 1, planet 2. So you can compare two planets to figure out, well, if I know this is the theoretical distance away something is, well, what's the theoretical period for that planet? So here's a little bigger version of it, just so you can kind of see. So if I had let's look at good old Pluto that used to be a planet down here. So Pluto has a period of 248.54 years. Its semi-major axis is 39.53 astronomical units. So when I square the period, I get 61770. When I cube the semi-major axis, I get 61770. Pretty much the same value, right? Exactly, almost. So if I divided those over each other, I get 1. If I go to Earth, 111, I get 1. If I go and now look at Mercury, the squared and cubed, 0.06 over 0.06 would be 1. So we see that for the Sun, the way we defined everything based on Earth, the relationship becomes kind of 1. Now, the one other kind of cool piece is gravity is, well, how do I get away from something if gravity keeps acting? And it falls along this idea of the satellite and the orbits. And it's the idea of this escape velocity, which is the lowest velocity that a body, an object, whatever you want to call it, must have to escape the gravitational attraction of a particular planet or object. And we calculated assuming that the desired distance we're trying to get away from that planet is infinity, and that we're trying to escape something called a gravity well. So we act like being near that planet is like being at the bottom of a well, and that the height of the well is infinity, and we're trying to get to the top of that infinitely deep well. And if you do the math out with how much kinetic energy you'd have to get to infinity, we're able to calculate how much energy we need to get out of the well. So our first probe that actually escaped the solar system was Pioneer 10, which we launched in 1972. And it's still out there, keeps on going and going and going.